Hi, I'm John Merritt, Director of Applications Engineering at Ideal Power. Today, Mike Barron, Senior Firmware Engineer, and myself will be demonstrating the advanced microgrid features of our 30 kilowatt Stabiliti multiport power converter. All of our demos were recorded in Ideal's Research and Development Lab located in Austin, Texas. The 30C3 converter has a 3-wire, 3-phase, 480 volt AC power port and 2 DC power ports, enabling high-efficiency solar and storage microgrids in one compact enclosure, which weighs about 140 pounds. Multiple 30C3s may be paralleled to support larger microgrid applications. Our demo setup utilizes 4 30C3s in 120 kVA nameplate configuration. So we created this third demo in response to some questions asked by customers. And those questions are, explain to us your master-slave relationship. You must have some means of these converters communicating amongst themselves, telling each one how to share and when to share power. And in many microgrids this is the case, but in our case there's no master. There's no master-slave relationship. We negotiate load through some droop algorithms. We use frequency droop to manage real power and voltage droop to manage reactive power. So each converter basically communicates by droop, voltage or frequency, to ensure balance between the 4 systems. Now, what we'll do is we'll start up with a small 24 kilowatt real load and a 16 kVAr reactive load. Purpose of that is to show that a converter can support that load, which is about 80% of its nameplate. We then can add converters, 2, then 3, then 4, and we'll see the power sharing between the 4 look quite similar to what we've seen in previous demos. And then we can take converters offline one at a time, and we'll see load sharing in the opposite direction. The last step is the one we started at. We've had customers say, well, that must be the master since you started with him first. So the last part of this is shut him down and watch the remaining 3 carry along merrily. No master-slave relationship.
Okay. So I'm going to bring on one at a time then to get us started. We'll leave this running in the background. So I've started up just one unit, which is the one where the plot lit up down here. So this is unit number 1. And you can see is already starting to register the power on the right. And if you look up here, you can also see that he's carrying the entire 24 kilowatt load by himself. So that one unit is doing all the work for the microgrid. The other 3 are not participating at all in the microgrid right now. Now we're going to bring on a second unit. Immediately that one will light up, and what you can see right now is the power is shifting. Over a period of about 3 seconds it rebalances. We now have 12 kilowatts and 12 kilowatts on each unit. Both the real and the reactive loads are evenly divided between the 2 units. And now we're going to bring in a third one. And again, they shift the power almost immediately, and we've got 3 units carrying 8 kilowatts apiece, whereas before we had 2 carrying 12 kilowatts apiece, and before that, a single unit with 24.
Now what's important about this is the ability for a converter to re-enter the grid and participate in this load sharing algorithm. And the timing, getting that timing right was one of the key things that our team of developers, including Mike, figured out. So not only do we have this droop algorithm that when all 4 are alive, they share load, or all 3 are alive, we need the ability for one to join up. And so this gives us system level redundancy.
So I'll go ahead and start up the 4th one, and once again you'll see they'll immediately shift the power. Now we have 4 of them, each carrying 6 kilowatts. None of these is a master. There's no master-slave relationship. So what we're going to do now is we're going to take out of play the first one that started everything.
And again, this answers the question, who's the master? Because we've had people say, oh, the first guy started was the master, and the answer is no. We can shut him down as well, and the remaining 3 play well together. Key part of the load sharing algorithm and synchronous entry and exit to the microgrid.
So we've shut down number 1, and at this point the remaining 3 have once again divided the load between them, so they each have 8 kilowatts, but it's the 3 that are still part of the microgrid. The one that started everything is no longer participating in the microgrid.
Mike, could you shed one more and see if we can capture that transition when we go from 3 to 2?
I will try to do that, John.
Now, there's not much load here, so this might be hard to see, but we're basically going to take one out.
It's very faint, but you can see it. And the only reason I can tell that it's there, John, is I'm just looking at a high level at the voltage. There was a very tiny droop of voltage when it dropped to 2 units instead of 3. But if you zoom in and look, there's no anomalies, no distortion of the voltage or the current waveforms.
Thanks for your time today. We really appreciate you dialing into this microgrid demo. Please contact us if you have any additional questions regarding our products or technology, and have a great day.